Hello friends, welcome back to my channel Engineering Mathematics DJ Ganit. In previous lecture we have discussed how to solve separable differential equations. Today also we are going to continue this separable differential equations and we will understand what is meaning of initial value problem. So first we try to understand the meaning of initial value problem. So sometimes we will be given some condition together with the differential equation. Suppose we have first order differential equation in this form and we are given some condition that value of y at point x0 is say y0. It is like for example, suppose we consider y dash equal to minus 3xy. This is the differential equation in which y is function of x. So x is independent variable, y is dependent variable, and we are given that value of y at x equal to 0 is say 1. So here we are given differential equation and with one condition. So differential equation together with this type of condition, the condition is known as initial condition. So differential equation together with initial condition is called initial value problem. Initial value problem means differential equation together with initial condition is known as initial value problem. Now as we know, if we solve this differential equation y dash equal to minus 3xy, there will be infinite number of solution for this differential equation depending on the value of arbitrary constant c in the general solution. Among all those solutions, we are interested in that solution for which value of y at x equal to 0 is 1. So here we will use this initial condition to determine the value of arbitrary constant from the general solution. So for initial value problem, we will always have particular solution. We will find out value of arbitrary constant in the general solution using this initial condition. So that solution whatever we will obtain, that will be particular solution. So solution of initial value problem is always of the type particular solution, and here we are discussing only first order differential equations. So we know that there is only one arbitrary constant in the general solution of first order differential equation. So we require only one initial condition. Suppose we are discussing second order differential equation, then there will be two arbitrary constants in the general solution of second order differential equation. So in that case we will require two initial conditions to determine the values of two arbitrary constants. That we will discuss as we proceed for second and higher order differential equations. Recently we are discussing only first order ordinary differential equations. So the initial value problem for first order ordinary differential equation will have only one initial condition. So differential equation together with initial condition is known as initial value problem. So here we have written the definition: a differential equation together with an initial condition is called an initial value problem. And if we consider x as independent variable and y as dependent variable, that is if our solution is function of x, then this is the form of initial value problem for first order ordinary differential equation. Y dash equal to f of xy, first order ordinary differential equation together with initial condition when x is x0, value of y is y0. So this x0 and y0 will be given. And as I discussed, the initial condition y of x0 equal to y0 is used to determine the value of arbitrary constant in the general solution. So we try to solve some initial value problems. Here we are given this differential equation y dash equal to minus y by x, and initial condition is y of 1 equal to 1. That is, when x is 1, value of y is 1. So the first step is we have to find out the general solution, and then we will use this initial condition to determine the value of arbitrary constant in the general solution. So first we write down the given equation. Given equation is y dash equal to minus y by x. Y dash is nothing but dy by dx. Dy by dx equal to minus y by x. And we can see this is easily separable. We take this y on left hand side with dy, and we shift this dx on right hand side with minus 1 by x. So this is separable ordinary differential equation, which is separable. So as we know, if our equation is separable, we have to integrate both sides with respect to x and y. Integrating, we get integral of 1 by y is ln y equal to integral of 1 by x is ln x, and plus arbitrary constant. But as we know, if we are having logarithmic function in each term, we can set arbitrary constant as ln c also. So this we can rewrite as ln y plus ln x equal to ln c, and using the property of logarithm, I can write ln y plus ln x equal to ln x into y equal to ln c. And as we know, logarithmic function is one function, so therefore we can write x into y equal to c, or this we can write as y equal to c by x. So this is general solution. We give this number 1, where c is arbitrary constant. So there are infinite number of solutions corresponding to different values of this arbitrary constant c. Among those infinite number of solutions, we are interested in that solution which satisfies this initial condition y of 1 equal to 1. So here when x is 1, y is 1. So we use this initial condition in this general solution 1. So using y of 1 equal to 1, that is we put x equal to 1, y equal to 1. In equation number 1, we have y is 1, x is 1. So from this we obtain that value of arbitrary constant which satisfies this using this initial condition is 1. So now we put value of arbitrary constant which we obtain in this equation 1, and we obtain the required solution. So therefore the solution of given initial value problem, that we can write shortly as IVP, is y equal to c by x. C is 1, so we have y equal to 1 divided by x. So this is particular solution corresponding to c equal to 1, and this solution y equal to 1 by x satisfies given differential equation as well as given initial condition. So the solution of initial value problem will never contain arbitrary constant. it will be a particular solution. So as we have done, we will first find out the general solution, and using the given initial condition we will find out the value of arbitrary constant. We consider one more example. Solve the initial value problem y dash equal to minus 2xy, and initial condition is when x is 0, y is 1. So first we write down given equation is dy by dx equal to minus 2xy. So we consider this dx on right hand side, we take this y on left hand side. So 1 over y dy equal to minus 2x dx. So now this is easily separable, so which is separable. So now we have to integrate both sides. Integrating, integral of 1 by y is ln y, minus 2 is constant, integral of x is x square by 2 plus c. C is integration constant or constant of integration. So this is minus x square plus c. These two will cancel out. And using the definition of exponential and logarithmic function, this we can rewrite as y equal to e raised to minus x square plus c, and again we can rewrite this as y equal to e raised to minus x square into e raised to c, and we can denote this e raised to c by c dash e raised to minus x square, where c dash is nothing but e raised to c. Now initial condition is when x is 0, y is 1. So we write down here using y of 0 equal to 1. So we put y equal to 1 and x equal to 0 in this general solution. So y is 1 equal to c dash e raised to 0 is 1. So we obtain that c dash equal to 1. So therefore now we put c dash equal to 1 and we obtain y equal to e raised to minus x square, and this is the solution of given initial value problem. So in this way we can find out the solution of initial value problem. Here we have first obtained the general solution, and we have used this initial condition in this general solution, and we obtain this particular solution of given initial value problem. This is the last example of this lecture. Solve the initial value problem e raised to x y dash equal to 2 times x plus 1 into y square. So given initial, first we write down given equation. Given equation is e raised to x y dash is dy by dx. This is equal to 2 times x plus 1 times y square. Initial condition is y of 0 equal to 1 by 6, that we will use after we obtain the general solution. So now we consider this e raised to x and dx on right hand side, and we consider this y square on left hand side. So we have 1 by y square dy equal to 2 times x plus 1 divided by e raised to x dx, and this we can rewrite as y raised to minus 2 dy 2 times x plus 1 e raised to minus x dx. So this is also separable, so we have to integrate, which is separable. So now we integrating we obtain, we write one more step, integral of y raised to minus 2 dy 2 times integral of product x plus 1 e raised to minus x dx plus constant of integration. Now integral of y raised to minus 2 is y raised to minus 2 plus 1. We write one more step, divided by minus 2 plus 1. Here we apply the integration by parts. If we recall, the formula for integration by parts is, if u and v are functions of x, we consider u as it is integration of v1 minus u dash, that is derivative of u, into integration of v1, that is v2, plus derivative of u dash, which is u double dash, integration of v3, and so on. And we consider that function as u whose derivative is 0 after some finite number of steps. So here we have two functions, x plus 1 and e raised to minus x. So we will consider this function as u and this function as v, because derivative of this x plus 1 will be 0 after some finite number of steps, but derivative of e raised to minus x will never vanish. So we consider u equal to x plus 1, v equal to e raised to minus x. So x plus 1 as it is integration of e raised to minus x, which is minus e raised to minus x, minus derivative of x plus 1, which is 1, and integration of this minus e raised to minus x, which is e raised to minus x. In the next step, derivative of 1 will be 0. So we stop here, plus c. Now we rewrite all these things. On the left hand side we have minus 2 plus 1, that is minus 1, and this is y raised to minus 1. And this is equal to, here we can take this minus e raised to minus x common. So we have 2 times minus e raised to minus x and x plus 1 plus 1. Minus e raised to minus x common. In the bracket we have left with x plus 1 and here 1 and plus c. We write one more step, x plus 1 plus 1 and plus c. This minus e raised to minus x is common, so we have 2 into minus e raised to minus x, and we are left with this bracket, and here we have 1 and plus c. So we can again rewrite this as this we rewrite as minus 1 by y. This is minus 2 e raised to minus x and x plus 2 plus c. So this is the general solution. So we give this number 1. Now we use the initial condition. Initial condition is y of 0 equal to 1 by 6. So we put x equal to 0 and y equal to 1 by 6. So using y of 0 equal to 1 by 6 in 1, we get, so y is 1 by 6, therefore minus 1 by y is minus 6. So left hand side we have minus 6, this is equal to x is 0, so this is going to be e raised to 0 1 minus 2 into 2, that is minus 4 plus c. or we can write one more step. X is 0, so minus 2 e raised to 0 is 1, 0 plus 2 is 2, so it is going to be minus 2 times bracket 2 plus c, and this is nothing but minus 4 plus c, so therefore c equal to minus 6 plus 4, which is minus 2. So value of constant is minus 2, which we put in this general solution 1. So in the next step, putting c equal to minus 2 in 1, we get left hand side is minus 1 by y equal to minus 2 e raised to minus x minus 1 by y minus 2 e raised to minus x into x plus 2 plus c, that is minus 2. So we obtain c equal to minus 2 here. Other things are as it is, minus 2 e raised to minus x, x plus 2. Now again we can rewrite this as minus 1 by y. We can take negative sign common, and we multiply this with 2, so we have 2x plus 4 e raised to minus x plus 2, and we take negative sign outside the bracket, and this 2 is multiplied with this, so we have 2x plus 4 e raised to minus x, negative sign is outside, so we have plus 2. So therefore now we can rewrite this as we take the reciprocal, y equal to 1 divided by 2 plus 2x plus 4 into e raised to minus x. So this is the solution of given initial value problem. We can check whether it satisfies initial condition or not. Initial condition is when x is 0, y is 1 by 6. So if we put x equal to 0 in this solution, we have 2 plus x is 0, that is 4, and e raised to 0 is 1. So our solution is correct. It satisfies this initial condition. So in this lecture we have discussed how to solve initial value problems, and we have focused on those type of differential equations which were separable, but the definition of initial value problem is same for all type of methods, either first order, second order, or higher order. So initial value problem means differential equation and initial condition. Differential equation together with some initial conditions is known as initial value problem. Now number of initial conditions will be equal to order of differential equation. If our differential equation is of order n, then number of initial conditions is equal to n. Now we are discussing first order ordinary differential equations. So order is 1. Therefore in first order ordinary differential equations we will have only one initial condition. If we discuss second order ordinary differential equations, there will be two initial conditions. So in this way we can solve initial value problems for first order ordinary differential equations. So this is all about this session. I hope you like this. Thank you very much.